Thanks all for coming. My name is Ivan Kostic, and I head security engineering and architecture for Apple. Really happy to be here and tell you about 3 iOS security mechanisms, one of which is new to iOS 10 in a pretty great level of detail. But before I do that, because everyone has been asking, let's talk about decrypted kernel caches. So as most of you know, sounds like by the laughter, in the iOS 10 betas, we shipped kernel caches unencrypted, and then in the subsequent beta, we actually shipped for pre-iPhone 5s devices, even iBoot and boot logos unencrypted. So yes, this is on purpose. We, from time to time, revisit the efficacy of some of our security mechanisms, and in this case, while doing some other optimizations, we took a look and realized that we could simply remove this encryption and not in any way impact platform security. So there is no impact to the encryption of user data. It was simply a way to do an optimization. And that's really all there is to it. So with that, let's talk about hardened WebKit JIT mapping. This is a new feature in iOS 10. And as background, so you understand where this is coming from, JavaScript on iOS in Safari requires just-in-time compilation to give really great JavaScript performance. But iOS as a platform normally enforces code signing on every executable page. So clearly this is a conflict. And in order to bring the JIT to Safari on iOS, we've had to relax the normal code signing policy and allow the JIT to emit new unsigned native code. And the way they used to work in iOS 9 is there was this 32 megabyte JIT memory region. It was readable, writable, and executable. And what that meant is that an attacker who had a write anywhere primitive that was exploitable from JavaScript could actually use it for arbitrary code execution, because they could take their shellcode, they could put it into the JIT region, and simply jump to it. On ARM processors, it used to be the case that the read bit for memory page protections was implicit. Every page was readable. But in ARM v8, that changed. They actually introduced support for execute-only memory. And we built the software side of this in the iOS 10 kernel. So what this lets us do is pretty interesting. We can now emit secret data into a page that the processor can execute, but the process itself cannot read. So what are we going to do with this? Well, we're going to take our JIT memory region, and that same physical JIT memory, we're actually going to create 2 virtual mappings. One of them is going to be executable. One of them is going to be writable. And the writable mapping will be at a secret location. Here's what I mean. We create these 2 mappings. We put the writable mapping at a random secret address. Then we create a specialized mem copy that actually has the address of the secret writable region as immediate values inside this new mem copy that we're emitting. We then make that mem copy execute only and discard the address of the writable mapping from elsewhere in the process. Now, we use this specialized mem copy for all of our JIT write operations. So here's the WebKit code that does this. The green shows where we actually mark our new mem copy as execute only. And then later on in the code, we simply zero out the address of the writable mapping from elsewhere in that process. So if this is hard to visualize, here's what it looks like. This is iOS 9, single region, read, write, execute. iOS 10, still one physical memory region, but 2 different mappings. The executable one on the left, the writable one on the right. And then in the red, you can see our execute-only page that has the specialized mem copy we've emitted. And the way this works is you call the mem copy with a buffer. This is what the JIT normally does. It uses the secret address of the writable region that's inside of it to actually move the buffer into the writable region. Because these are 2 mappings pointing to the same memory, that makes it appear in the executable region, to which we can simply jump. But the process, other than the memcopy function, doesn't know where the writable region is. So let me actually show you what this looks like. I have 2 phones here. And the one we're connected to right now, when the top piece goes away, here, let me show you here. So this is an iPhone running iOS 9.3. And if we look at the memory map for the web content process, which includes the Safari JIT, you'll basically see these 2 guard pages. And then you'll see one 32 megabyte region that's readable, writable, and executable. And this is our normal JIT region. But if I switch to the iOS 10 phone, it looks a little bit different. We still have our guard pages, but we now have one mapping that's executable, one mapping that's writable, and we have this execute-only mapping. So let me show you what's in there. I'm going to attach a debugger to the web content process. And we'll take the address of our execute-only region and see what's there. So what we do here is, as immediate values, we'll encode the address. Here, read this from the bottom up, 1708A, C000. That is the address, if I scroll up, of our writable region right there. And then the rest of this is effectively just the mem copy you would expect. And the way this works from inside the process, if we take a look at, for example, the readable and executable region, and from the context of the process, we attempt to read what's in it, that will succeed. It'll return 0 error code. But if I take our execute-only mapping, which has the memcopy function, which includes the secret, that simply fails. Bad access exception. The memory is not readable, only executable. So where this gets us is that an attacker who simply has a write anywhere primitive from the context of JavaScript can no longer use it by itself for arbitrary code execution in the process. Instead, they have to subvert control flow, usually through ROP or a similar mechanism. It's kind of a nice mitigation that raises the cost of exploiting memory corruption bugs, in particular in WebKit. So I want to move on to the second feature I'm going to be talking about, which is data protection, and specifically how it uses the secure enclave processor in iOS devices. Data protection is the name for the feature that protects all user data at rest on our devices. And when we set out to design this, we had a pretty clear set of goals in mind. We wanted user data to be protected with strong cryptographic keys, no offline attacks, which meant that the keys protecting user data had to be bound to the hardware, no brute force, so hard limit on the number of incorrect passcode attempts. And we wanted to build something that could be used as a base for secure alternative unlock mechanisms like biometrics in Touch ID and the auto unlock feature, which is new to macOS Sierra and lets you unlock your Mac from your Apple Watch. But we also had one more goal, which is to entirely sidestep the attack surface for the AP. This is the application processor. This is the normal CPU that runs all the rest of the code in the operating system. And so what does this mean to sidestep the surface? Well, it means that the authentication policies that I described, such as our hard limits, they need to apply even under an adversarial AP. And no long-term key material should ever be exposed to the AP. Any short-term key material that's exposed needs to be ephemeral and needs to be bound to the session, which means it basically stops being valid after the device is rebooted. So the way we set out to do this is we introduced the secure enclave processor, which is dedicated silicon running a small trusted computing base that serves as our cryptographic coprocessor. It has hardware accelerated crypto on it, and is the arbiter of all user data access on these devices. It has its own encrypted memory, has a very narrow interface with which it communicates to the normal AP. And in the factory, we actually do key pairing so that the SEP has secure channels to both the Touch ID sensor and the secure element, which is what's used for Apple Pay transactions. The SEP also has a true random number generator on board. This is free running oscillators. And the very first time the SEP is powered in the factory, it uses this true random number generator to generate what we call the UID key. This is a unique private key that will always stay within that enclave processor and is not exportable. In fact, the only way that the UID key can be used is through cryptographic operations that are exposed by the secure ROM, which is burned into the hardware at the factory and is not mutable. So no mutable software ever gets to see this key material, and it originated from within the core itself. Now that we have the UID key, that forms the root device key that will be used in deriving all the rest of the keys. And when it comes to keys that are actually used to directly protect user data, we group them in what we call user key bags. So user key bags are sets of keys generated for each user, And they're wrapped by a master key, which is derived from a combination of the user passcode and the UID key in the hardware. So this lets us make the case that after 10 incorrect passcode attempts, the SCP will simply refuse to process any further attempts. And so long as it refuses to do so, as it's the only thing that can ask for cryptographic operations to take place on the UID key, it is not possible to make any more attempts. Now, for the user keyback keys, I mentioned it's a set of them. This is because they're used for different purposes and they're available at different times. So this is effectively the key list. They're class keys. We call them A through D. And some of these are keys that are always available when the system is running. And then some of them are only available after the user has unlocked their device at least once. And yet class A is stronger. These are only available while the user is actively using the unlocked device. Now, mind you, classes A, C, and D, these are 256-bit AES keys. For class B, it's actually a key pair with curve 25519. And what that lets us do is make the public key always available, but the private key is only available while the device is unlocked. So I'll explain about that in a moment. Meanwhile, here's, just in case you're curious, what an actual annotated key bag looks like. This sits on the file system of every iOS device. Just tells us the version, the KDF salt, the iteration count used to derive the keys, and then actually has the key identifiers for the wrapped keys themselves. And in the case of the class B key, the raw bytes of the public key for class B. So I mentioned that the master key is derived from a combination of the user passcode and the UID key. This is a very straightforward process. Effectively, we take the user passcode and the salt in userland, we run it through a key derivation function, and then we move it over to the hardware side where the SCP will continue iterating on it using the UID key. And the number of iterations is chosen to meet a time goal, which is between 100 and 150 milliseconds. So we want it to be the case that the derivation takes a certain amount of time. So now that you understand how the keys work, the question is, how do we use this to actually protect file system data? File blocks themselves are encrypted with AES-XDS with 128-bit keys. But the thing to know is that each file actually has its own unique random key that is generated by the SCP for it. And those raw file keys are never exposed to the normal application processor. Instead, they're wrapped with a key from the user key bag for long-term storage. And remember, those keys are can only be unwrapped by the SCP. And then while the system is in use, they're also wrapped with an ephemeral key that is bound to that boot session of the phone. So this is kind of an interesting thing to think about. Let me show you what it looks like. At boot of the device, the AES engine in the SCP generates an ephemeral key and through a secure out-of-bound channel sends it to the storage controller. This is the NAND controller for the unit. Then later, when the phone is running or the device is running and you attempt to open a file, the kernel will fetch the wrapped file key from the metadata, will send it over to the SCP, which will use the user keyback key to unwrap it, and then it'll rewrap it to that ephemeral key that was chosen at boot. And it's this ephemerally wrapped file key that is sent back into the kernel from where it's sent into the storage controller, which can now use the ephemeral key to unwrap the real file key, retrieve the ciphertext from the NAND flash, and send the clear text back into the kernel. What's important about this is if you look at the keys that are exposed to the kernel, none of them have any long-term value. After the device is rebooted, that ephemerally wrapped key simply serves no purpose. So hitting the goals we set out for data protection actually requires quite a few moving parts. And I wanted to walk you through what it actually looks like when a device boots, when a device is first unlocked, when it's locked, and then finally when we use a Touch ID unlock. The first thing that happens is that the kernel boots, and this is coming off the system partition. And the Apple Key Store will load what we call the D key. This is the class D key out of effaceable storage. And effaceable storage is, if you're not familiar with it, a part of our NAND flash where we allow no wear leveling and no relocation of blocks, which means we can securely erase things that are in that section of the flash. So this D key is retrieved and sent into the SCP, which decrypts it using the UID key and hardware. and loads it into the SKS keyring. SKS is the application on the secure enclave that handles our data protection keys. It's called a secure key store, or secure key service. And so now this decrypted class D key is loaded into the keyring. The kernel will decrypt file system metadata using a media key. Media key is another key that's stored in effaceable storage. And at this point, launchd kicks in, mounts the user partition, and starts a daemon called keybagd. Keybagd loads the system keybag, which is just sitting as a file in the file system, and it can do so now because our class D key is available. Decrypts this keybag using yet another key from effaceable storage called the protection key, and sends it into SKS, where finally the device keybag can be unwrapped, the class B public key loaded into the keyring. So if you look at what this means, normal class keys, A and C in particular, and the private key for class B, those are not decryptable until the user can present their passcode and the master key can be derived. But the device in this state can read all class D protected files and can use the class B keys to write files that are only readable after the user unlocks the device. It's kind of a Dropbox mechanism. After this, launchd will simply permit user space to continue booting. Now let's talk about first unlock. First, Springboard, which is the user-facing user interface on the device, will acquire the passcode from the user. And it'll send it to the SEP, which will generate the master key using a combination of the passcode it just received and the UID hardware key. Now that we have the master key, we can take the user keybag and decrypt all of the class keys and add them to the keyring. But we'll do one more step. We'll take our master key, we'll generate a random secret, and we'll encrypt the master key with that random secret. The random secret will be sent to SBio, which is another app running on the SEP, which is responsible for doing biometric matching for the Touch ID sensor. Mind you, it's not the master key or even the encrypted master key that's sent over, just the random secret. It's SKS that still holds on to the master key encrypted with that secret. After this, SKS will securely destroy the master key, the raw master key from its memory, holding on only to the encrypted version with the secret that it sent to SBio. And you'll see how we use that in a second. But first, because lock is simple, let me show you what happens here. Once the device locks, we simply notify the SEP, it purges the class A and B private keys from its keyring, and that leaves the public key for class B, class C, which if you remember is meant to be accessible anytime the user has unlocked the device at least once, and finally the class D key. So here's how Touch ID works in this model. Pressing the home button starts the sensor, and the sensor acquires an image and sends it to the SBio app in the SEP. This app actually performs the match and determines whether the fingerprint that was just acquired matches the fingerprint of the authorized user. If so, it takes the random secret that we handed it earlier and sends it back to SKS, to the secure key store. That lets SKS decrypt the master key yet again, and upon that, decrypt all the rest of the class keys and add them to the keyring. After that, the raw master key is once again securely destroyed. I want to mention one more thing, which is that data protection and how it interacts with the secure enclave also enabled us to securely do a feature called Update Later, which is basically that when a user logs in and unlocks their device, they're notified that there's a software update available, and they can choose to do the update right then and there, but they can also say install later. And if they choose install later, we'll prompt them for their passcode, and if we can verify that it's the correct one, we will enable the creation of what we call an OTUT. This is a one-time unlock token, and it's a token that the SEP creates. After this, the user is going to log their device, but once the user said install later, we use on device the same predictive technology that underlies our proactive assistant to make a best guess of a time of day when the user is not going to be using their device and the device is going to likely have power. So once we've made that prediction, the user is interacting with their device over the course of the day, and at some point they'll have unlocked the device, and based on our prediction of the right update window time, we will conclude that this is likely the last time they're unlocking their device before eventually they will hit the update window later. So because of this, and because we enabled creation of the OTUT earlier, we will actually create an OTUT at this time. The software update subsystem will say, there's an OTUT created, please persist it for me. And it'll also start an 8-hour timer. If an OTUT is not used for 8 hours, it'll be destroyed. And the user, none the wiser, is continuing to use their device and will at some point lock it and probably go to bed. But at this point, we're persisting that OTUT, which means that when we hit the update window time, in this case, we guess that 3 a.m. is a good time, the software update can run on the device. And after it's finished, it can reboot the device and use the OTUT to unwrap access to user data once again to finish doing things like migrating data if required by the new software update, so that when the user next goes to use their device, rather than a software update having taken place and their device being fully locked as if they had rebooted it, instead they get a fully working device ready to go with the latest software on it. There's one more thing I want to call out about this, which is something we call the SoC security mode. We have a feature called demotion, and this is because if you think about it, we have 1 billion active devices out there, and we need to have some ability to be able to debug a production device. And so the demotion feature is a way to take a production device and enable some debugging functionality like JTAG and the ability to load development software on the application processor, though not the SEP. This requires both that after being authorized for this on the personalization server, the device to be demoted is fully erased and a new OS loaded on it. But the key thing about it is that it also forces a different UID key to show up to the SEP, and this is done in hardware. In other words, if a production device is demoted, the UID key that was used in deriving the master key that protects any user data previously on that device is simply unavailable to any software. A different UID key turns up. So if you remember the goals that we set out for ourselves for data protection, this is how we managed to meet every single one of them. What I want to talk about next is synchronizing secrets. We have a number of features where it's really, really useful to be able to move the user's secret between their different devices. Passwords and credit card information for Safari are a good example, but also some new features like auto unlock, which I mentioned earlier, which wants to be able to securely move cryptographic keys between a user's Mac and their Apple Watch. And then HomeKit is another good example where we want all cryptographic keys to be available on all of the user's devices so they can control their HomeKit devices. And of course, there's bound to be many more uses for the ability to do this. And if you look at how synchronizing secrets has traditionally been done, there's basically been two approaches. Either you generate a strong random key that's going to be protecting all the rest of the secrets as they're moving, which means that usually the user has to print a key or write it down, and so it has the right cryptographic security level, but not an acceptable user experience. Or the second option is to derive a key that'll be used to protect the rest of the secrets from the user's password, which is a problem because users tend to not choose cryptographically strong passwords. And if this is a password that belongs to some account they have, it usually means that the account provider backend is in a privileged position. They may be able to brute force the password and therefore access all of the user's secrets as well. Why don't users just pick strong keys? Well, this is from a book on cryptography. Humans are not very good at this. So when we looked at synchronizing secrets and what the goals are for a mechanism to do this, we were actually pretty inspired by what we've done with data protection. We wanted selected user secrets available on all devices. We wanted strong cryptographic keys protecting them. We wanted the user to be able to recover this even if they lose their devices without having to write down a key and put it in their sock drawer. And we wanted the user secrets to not be exposed to Apple at any point. We also wanted no brute force ability. So here's how we approach this. With iCloud Keychain, we have every device that participates generate an iCloud Keychain synchronization key pair. This is a strong key pair. And when a user has a new device that they want to have receive their secrets, they actually have to explicitly approve it from a device that they already started with. And once that happens, the devices can start receiving all of the rest of the secrets. Now, the way this synchronization circle works is it uses the Apple Cloud backend for message passing and for storage, but the backend is in no way in a privileged position because, again, this is protected by what was a locally generated strong key pair. So this is one part of the story, but what if the user loses all of their devices, or what if they need to configure a new device without actually having access to the old one? So for this, we have a feature called iCloud Keychain Backup. And here's what we do. We have a new credential, the iCloud security code. And most often, this is the device passcode, the passcode of the actual device. This is a credential that's clearly unknown to Apple. We then generate a strong random key, which we call the escrow key. And we will wrap this escrow key with a key derived from that iCloud security code, most commonly the device passcode. We then take the wrapped escrow key, send that to Apple, and we back up a copy of the iCloud Keychain secrets that are encrypted themselves with the escrow key. Now, if a device is lost or the user has a new device but no access to the old one, they can recover their secrets so long as they have their iCloud password and this new credential, the iCloud security code. So if we look at the goals that we have for synchronizing secrets, we meet the first four with a combination of iCloud Keychain and iCloud Keychain Backup. But what about that last one? The attack surface on the back end here is quite tricky. If we implemented naively what I just described, the backend is clearly in a position to brute force the iCloud security code and access the escrow key. Remember, the iCloud security code is most commonly the device passcode, which means only a million possibilities, usually. And so what we need is, just like with the secure enclave, we need some way to enforce a policy over the escrow key that prevents brute force and does so even under an adversarial cloud. So we said, what if unwrapping the escrow key could only take place in hardware security modules? Let me tell you about Cloud Key Vault. Cloud Key Vault is just an internal name for a collection of hardware security modules, which, if anyone is not familiar, they're cryptographic coprocessors that can generate keys securely within the hardware that are non-exportable and just expose cryptographic operations on them. We have a fleet of them that are running custom secure code within the hardware security modules themselves, and these are connected to the Apple Cloud. The Key Vault fleet operates its own certificate authority, where the private key never leaves the hardware of the hardware security modules. And each iOS device hardcodes the certificate of the Key Vault fleet. This is the simple unit for Cloud Key Vault. It's a host paired to a hardware security module, and then the hardware security module has access to a number of keys. Most importantly, the first one, which is the custom secure code signing key. So this is a code that allows software to be loaded into the hardware security module. And then lastly, that service key, which allows unwrapping the user's escrow records. So what's an escrow record? I mentioned earlier. It's the user's strong randomly generated escrow key. It's an SRP verifier for their iCloud security code, commonly device passcode. And then it's a maximum failure count of how many incorrect attempts on the iCloud security code are allowed within the context of this record before no further attempts are allowed. So this escrow record is encrypted to the public service key for the Cloud Key Vault. Where does this get us? Well, we've effectively built a kind of data protection, but for escrow records. The private key for the Vault service is simply not available to any mutable software, just like our UID key in the SCP. And effectively, when a user wants to do an escrow recovery, they retrieve their escrow record from the Apple Cloud. They establish a session to Cloud Key Vault for SRP. And the Vault will unwrap the record, find the SRP verifier for the iCloud security code. So long as the user can present the right iCloud security code, the Cloud Key Vault will return that strong randomly generated escrow key, which protects all of the rest of their secrets. And if SRP fails, the Vault unit bumps a secure counter, where if a maximum failure count from the record is reached, the record is marked terminal, and the Cloud Key Vault will refuse to process any further attempts with that record. The thing is that a user can't simply escrow to only one key vault unit. We need the redundancy in this design because these units can fail. But if we simply said, well, why don't we escrow to 5 units? That's because every new unit you escrow to increases that maximum failure count. If you escrow to 5 Cloud Key Vault units, then instead of having 10 maximum failure attempts, you're now up to 50. So here's what we've done. We've paired the Cloud Key Vault units into clubs that actually, these are clubs of 5, and they share a single service key. So the user generates their escrow record targeting a specific club, and that club is certified by the Fleet Certificate Authority. This solves our redundancy problem because now we have 5 units, but it doesn't solve brute force limiting because club members could still be attacked with partitioning attacks. This simply means if you have a club of 5, one of them can be isolated from the network, and then you make 10 attempts on it using the escrow record. If that doesn't work, you move it aside, you isolate the next one from the club, and you repeat the process until ultimately you've gotten the maximum failure count multiplied by the 5 units in the club. So what we've done is implemented a quorum commit scheme where each club actually maintains its own failure count. Each club member maintains its own failure count for each escrow record. And when an escrow recovery is in progress, it actually prompts a vote where a majority quorum is required to proceed. So this provides both redundancy and breaks membership partitioning attacks. Here's how it works. This, by the way, is the overall Fleet design. So the Fleet is partitioned in these clubs of 5 units. There's authenticated object storage in the back, and then there is an iCloud escrow service proxy in the front. So here is what an escrow transaction looks like. Effectively, one Cloud Key unit out of the club is chosen as the originator and says, I propose an update. Please give me your failure count for a specific escrow record. The rest of the units say, here's my counter. I vote yes on this update because I'm not in another transaction, so I can do this. Then we move to the next phase where the originator says, very good, we have majority quorum. No one's record is terminal, so prepare to update the failure counter to 5. All the rest of the club members say, very well, I've verified that we have majority quorum. I stand ready to increase the counter. After that, the originator says, excellent, increase the counter. And finally, all of the rest of the club members confirm that they now have the new failure count of 5 for this record. Now, I mentioned that there's this custom security code signing key that lets you sign any software you want to have running on these hardware security modules that power the Cloud Key Vault. And the way to use this very powerful key requires an actual physical quorum of smart cards. So when we create a new fleet, there's a secure ceremony where the 3 admin cards that can unlock the CIK are put in tamper-resistant evidence bags and are handed to 3 different organizations at Apple, which then store them in 3 separate physical safes. But yet, if someone managed to get their hands on all of the admin cards, they could put them together, sign a new custom secure code image that can bypass all the protection I described and brute force the iCloud security code for any arbitrary escrow record. Couldn't they? No. Let me tell you why. Before a fleet goes into production, a Cloud Key Vault fleet, the members of those 3 card-carrying organizations at Apple meet in a secure facility. They cross-check the serial numbers on all the evidence bags from the original ceremony and the cards within them. And then they make a series of attestations that are recorded. They attest that they were present when the cards were created. They attest that no other admin cards were created, that the evidence bags have been sealed the entire time, and that the cards that are present today are exactly the cards that were originally created. And then the cards are combined using a novel physical one-way hash function. This is our crypto blender. Thank you. I thought you might like that. After this is done, a number of final attestations are recorded. All the people present attest that all the cards that were originally created are now destroyed, that the cards were not in the interim used to sign any other custom secure code that can be loaded into the fleet, and finally, that no other mechanism is known that would allow the custom secure code to be changed or new code loaded. Why do we do this? Why take that last step that's extremely unusual? We've seen with data protection in the secure enclave processor that we go to tremendous lengths when it comes to engineering these security systems that provide trust in how we protect user data. But we realize that when data leaves the device, the stakes are even higher. And we're fortunate that we've earned the trust of our customers, but we realize that that's something that we have to keep earning. So here, when we make a statement like, your secrets are not exposed to Apple when they're being synchronized, we have to be able to make it unequivocally. And if we still retain possession of these admin cards, there's the possibility that that's not true. So because of that, we destroyed the cards. And I hope that gives you some feel for how seriously and how passionately we take our mission to protect user data. So those are the 3 features that I wanted to talk about today. And before we move on, I want to share some news with you. I'm very happy to say that Apple today is announcing an Apple Security Bounty Program. Thank you. We've had great help from researchers like you in improving iOS security all along. And as the security mechanisms we build, such as some of the ones that I've been describing to you today, have gotten stronger, feedback that we've heard pretty consistently, both from my red team at Apple and also from researchers directly, is that it's getting increasingly more difficult to find some of those most critical types of security vulnerabilities. So the Apple Security Bounty Program is going to reward researchers who actually share critical vulnerabilities with Apple. And we're going to make it a top priority to resolve these confirmed issues as quickly as possible. We'll provide public recognition unless asked otherwise. And let me tell you where we're starting. This is our list of initial categories. We believe that these payment amounts are commensurate with the level of difficulty in attacking some of these systems. You'll see that there are 4 categories for on-device vulnerabilities and 1 for any unauthorized access to iCloud account data on Apple's servers. In addition to these exact amounts, we will let researchers donate the reward to charity of their choosing. And if they do so, we will, at our option, match that 1-for-1, doubling the donation. And I mentioned that these are all maximum payments. The exact payment amount will be determined after we on the engineering team review the actual report that is submitted. This has to be a clear report with a technical proof of concept. It needs to show the vulnerability present in the latest version of iOS and on the latest hardware where that's applicable. And we'll look at both novelty for a vulnerability and also the likelihood of user exposure. So frequently, how much interaction is required from the user to actually exploit the vulnerability. And we know that there could be important vulnerabilities elsewhere, but this is where we're starting today. So the program goes live in September, and we're inviting a few dozen researchers to participate initially. This is because we want these interactions to be really great. But it's not meant to be any kind of exclusive club. So if someone who is not in the program brings to us a vulnerability that would be covered under the program, we welcome that. We're going to take a look, and if the work merits it, we'll invite them into the program, and we'll reward the vulnerability that they found. Very happy to get this off the ground, and so pleased to be able to tell you about it today. Thank you very much, and I'm happy to take some questions. All right. Go ahead.
Just quickly, to what extent has the problems you've been having with the FBI trying to unlock devices influenced your security architecture going forward in iOS 10?
I'm an engineer. I'm happy to answer technical questions about what I've covered today. Go ahead.
Hello. So maybe I just missed in some way. Is there any mechanism by which a user can audit, possibly revoke the list of devices that have been given trust access by his other devices? I'm imagining situations where somebody has a friend of mine, for instance, had a phone sitting unlocked on a counter and then walked away momentarily. Somebody could set it up, trust to their devices, and suddenly their key bags and everything are just being synced across constantly, permanently.
Key bags are definitely not being synced.
I'm sorry. I'm just standing up in front of a microphone, being kind of nervous here.
Not a problem. So for iCloud Keychain, it's sufficient to change your iCloud password, and that'll actually break the pairing. Some of the details for that, I believe we have in the iOS security guide, which is a public document. And if you find any part of that doesn't answer your question, shoot us an email, and we'll see if we can get you an answer.
Can you get a list of those devices, though, so that you know if you need to revoke them?
I see. No, that is not available right now.
OK.
Go ahead.
Hi. What is the reason why you're doing this now? I mean, you've had many software updates, and this is the first time that you're talking about your data protection program. And also, why is now the time to release the Bounty security program?
Well, it's not the first time we're talking about this. The iOS security guide, which again is a publicly available document, goes into it hits most of the outline of the design and how it interacts with the secure enclave. What I've done today is offered, I think, a lot of new detail that I thought would be particularly interesting to a super technical security audience. But it's not our first time describing how our security works. And in fact, the guide is now quite long and gives a pretty comprehensive overview of virtually every single security mechanism that we have. As for the Apple Security Bounty Program, I tried to sort of answer that by saying that the feedback we've been hearing pretty consistently for some time now is that the difficulty in actually finding some of these most critical kinds of vulnerabilities has been going up and up as we've continued to invest into technical security mechanisms. And so the difficulty of finding these now is such that we want to reward the people who spend the time and effort and, frankly, creativity to be able to still find vulnerabilities in some of these categories. Go ahead.
You mentioned how the secure enclave that you described today and the secure element for Apple Pay are separate hardware modules. Can you speak as to why, like the history as to how that came to be, why wasn't Apple Pay just developed on top of the secure enclave? That's a pretty hard question, and I'm going to focus just on what I covered today, if you don't mind. But again, feel free to shoot us an email, and we'll see if we can get you an answer. Yes.
Hello?
Hi.
Oh, over here. Other way. Are your systems, are your cryptographic methods 140-2 validated FIPS?
Sorry, who's talking? Aha, I see you. I think the exact status of the FIPS certification should be mentioned in the iOS security guide. Essentially, some of it is validated and some is not.
OK, thank you.
Mm-hmm. Uh-huh.
All right, you go ahead and try.
Yep, I hear you OK.
OK, you hear me?
Yep.
So after you destroy that code signing key, is there any way to update the firmware or the software running on the cloud?
There's not. In fact, that's the very purpose of destroying that signing key. So go ahead.
So what if there's some vulnerability that's discovered later? Do you have to wipe out the entire farm, the entire fleet, and restart?
If a critical vulnerability were to be discovered in the Cloud Key Vault fleet, we would have to stand up a new fleet that has the patch software, and then over time migrate new user enrollments to that fleet.
OK, thank you.
Go ahead.
So in keeping with that story of the extreme methods measures you're going to protect users from misuse of key material that Apple might have, can you talk to us about mitigations that might be in place to keep the secure element from ever being forced to run software that would divulge the key material it has?
I think you mean the secure enclave rather than the...
Forgive me, yes.
The software that runs on the SEP is covered by the same secure boot chain that validates all the rest of the software that's running on iOS devices.
I understand if that's all you're willing to say.
Thank you. Okay, we have someone in the back. Go ahead.
So with the Apple Watch, if you can unlock Macs and phones, and if I lose that Apple Watch, how do you protect all of the other accounts that I have?
All of the other accounts, you said?
I mean, all of the other devices. So if with the Apple Watch, if I can unlock my Mac, and if I lose that Apple Watch, what kind of security?
Yeah, it's a good question. So I don't know if you do you use an Apple Watch?
No.
Haha. If you did, you would know that when you set up your Apple Watch, you actually have to pick a passcode for it, and you can set up your phone to effectively help you unlock your watch, but the watch has a sensor where the moment you remove it from your wrist, it'll lock. And once you put it back on your wrist, you can either unlock it using your phone or you have to enter a passcode directly into the watch.
Follow-on question from what you said earlier. So if the case that you have to migrate over to another fleet, what mechanism is there to prevent, say, FBI migrating everybody's data, escrow keys over to their fleet and effectively own
There
everyone?
is no ability to migrate an existing record to a new fleet. That's simply not possible. What we can do is stand up a new fleet and migrate new enrollments into that fleet. So in other words, the existing body of escrow records can only ever be decrypted by the club that the user created the escrow record to. What we can do is make it so that further enrollments can go into the new fleet. And that, by the way, requires the CA cert for the new fleet to be present on the iOS device. So it has to come through a software update.
So then existing phones, existing devices will continue operating with the possibly compromised or older software fleet?
They will use the best fleet that's available to them given the software version that they're running.
I see.
We have tremendous uptake on our updates. More than 90% of our user base is using the latest version of iOS, so that's a good place to be.
All right, thank you.
Go ahead.
For the 10 passcode attempts before it falls out, is that enforced in the SEP, or is that value stored outside of the SEP?
It is enforced fully in the SCP. The SCP has a secure monotonically increasing counter.
Okay.
And if that counter reaches 10 incorrect passcode attempts, it will simply refuse to use the UID key any further for that user key bag.
Okay. So it's not stored in memory or anything like that. It's all in SEP.
It's fully within the SCP.
All right. Thank you.
Yes.
With all the research around making fake fingerprints and being able to duplicate a human fingerprint based on like a fingerprint record, and you look at the OPM breach where all these fingerprint records were stolen, it seems kind of scary that like a touch ID sensor, someone may be able to reproduce a fake finger and then get into a device within the 48-hour window. Is there any thoughts around some sort of mitigations to mitigate, malicious fingerprint scans, or maybe even make it configurable to reduce that 48-hour window to something a little bit less, at least for an end user, make it configurable?
It's an interesting question. I think for biometrics in general, I think these vulnerabilities are to some degree inherent, and we do the very best we can with both our sensor and how it's used. You saw that we make all the template matching happen in the secure enclave. None of that ever touches the application processor. That said, we continue to follow the research that's happening in that space, and certainly would continue improving as best we can over time.
Thank you.
Go ahead.
Hi. Would you be willing to talk about the upcoming features of Watchtower in iOS 10 and a bit of the design of that structure?
I'm going to focus on what I talked about today.
I was wondering if you'd be willing to talk about any of the mechanisms against side channel attacks you might have, so in particular EM or power or sound.
I'm not sure what of that we discuss in the iOS security guide. I think if we don't cover that, that would be an interesting thing to consider adding. So please shoot us an email, and we'll see what we can do. Go ahead.
Yeah, I was just curious, what's the most persistent security issue you face with iOS in general?
Tough audience questions. Thank you. No, really though, thank you. Go ahead.
Yeah.
I'm coming from the Chinese team, and where team is Niwan team is focused on Apple secret research. And from last year to now, we feedback some secret problem to Apple security. But we have a problem because we find the secret Apple secret feedback response is too slow. So, and maybe one secret problem to about 1 year. So how can we solution this problem?
I'm sorry, I didn't quite follow your question. You're saying that which part was slow?
Yeah, we feedback some secret problem to the Apple security, but the Apple security is response too slow.
I see. The question was security response. You know, we get a tremendous amount of issues, and overwhelmingly, all of them are answered very quickly. If you have issues that for some reason you're having trouble with, please send another email. You should not be encountering that kind of issue. All right, folks, I think that's all we have time for. Thank you very much for coming again. I really hope you liked what you heard.